Hello, ladies and gentlemen, Root Beer here, and we are going to be finishing up our 2019 Euclid competition in this video. We're looking at question number 10. In fact, now we're looking at question number 10. And we've got three parts here, an A, B, and a C. All of it written, of course, but we should be prepared to maybe think outside the box a little bit, or something, or maybe in for some long calculations, because this is question 10. This should be the hardest thing on the Euclid. Okay, usually people don't even try 10. What do we got? Amir and Bridget play a card game. Amir starts with a hand of 6 cards, 2 red, 2 yellow, 2 green. Bridget starts with 4 cards, 2 purple, 2 white. Amir plays first, and they alternate turns. It'll go Amir, Bridget, Amir, Bridget, Amir, Bridget. On each turn, the current player chooses one of their own cards at random, so there's probably some probability going on here, and places it on the table. The cards remain on the table for the rest of the game. Player wins, and the game ends when they have placed 2 cards of the same color on the table. So it'll take at least until Amir's second turn to win, because that's the first time there will be 2 cards from the same player on the table. And we want what? Determine the probability, there we go, that Amir wins the game. Okay. So I think probably for this particular sequence of events, there we go, I prefer it not to be in continuous mode. For this sequence of events, we're probably going to want to try to use a probability tree. So probably going to abbreviate Amir with A, and he has 2 red, 2 yellow, 2 green, and Bridget 2 purple, 2 white. So it's very nice they didn't use blue or black, so I can just use this B with as much as I'd like. So a couple comments. First possible win is on A's second turn. Okay, so we'll start there. Okay, so what I'm probably going to do is I'm going to verbally explain the tree, and these are things that you would write down. I'll write down some of them, but there's only so much room I have on my pages, and I don't want to be flipping back and forth. So here's where we're going to start. So this is Amir's second turn. And so he can either win or lose, and that's what we're focusing on. Does he win? Does he lose? Because we care not about the probability that he lays his yellow card after laying a red card. We just care whether or not he wins. So he doesn't win, the game continues, right? Now, what are the chances that he wins? Because I need to know what probability to put on my tree. Okay? So, at this stage, and this is the sort of thing you would write, he has 5 cards. Okay. He has laid 1. He wins if this card matches the one he laid first. So it's Amir's first turn. He lays a red card randomly. So then he will have only 1 red card, 2 yellow, and 2 green left. He can only win if he lays that red card again. And the same sort of thing works if he laid a yellow card first. He's got a 1 out of 5 chance to pick the remaining yellow card. So it's really 1 out of 5. Now, you can hem and haw and choose to make this harder for yourself by saying, okay, well, suppose he picks a red card first, and then what's the probability the rest of the tree happens, and that he picks a red card second. Or you can realize that this is so far color independent. Okay? It doesn't matter what card he laid first. It's out of the hand, and there's a 1 out of 5 chance that he picks the remaining card of that color. So that's sort of initially how I'm approaching this. Now, it might be later on as we make the tree bigger and bigger, it becomes complex, and we do need to keep track of colors. But right now, I think it's a 1 out of 5, rather than a series of sort of 1 out of 15s for the various different colors he could have chosen. I don't think we need to do that quite yet. Okay? Now, the way probability trees work, if you've got 1 out of 5 here, the sums on the branches need to add up to the total probability, and total probability is 1. So it's a 4/3 chance that he picks any of the other cards. sorry, not 4/3, 4/5, and therefore does not win. And then it's Bridget's second turn, and she could win. Okay, so maybe she wins, or she doesn't. Now, how can she win? Again, if she matches, so she's laid the card, so she's laid one card. And it's interesting, her win has nothing to do with Amir's win. The only way Amir and Bridget affect each other is if one wins before the other. And it's not like they're playing cards off of each other or anything like that. So she's laid one card and wins if her 1 out of 3 choice, because say she lays purple, then she's got 1 purple and 2 white left. So she matches that card. So she can win on the second turn, not with probability 1/3, but with 4/5 times 1/3, because you need to know Amir didn't win beforehand. Okay, so we can fill in 2/3 chance that at this point, if it's on her second turn, it's a 2/3 chance she won't win. Okay, and then we might run out of space here, but then there's a chance that Amir wins. Okay, or not. Right? Now, if we're here, Bridget has laid down both a purple and a white card. Otherwise, the only way that it doesn't have to be that order. What would Amir have done? Well, suppose he did a red the first time. He can't have laid a red here. Maybe he lays a yellow. So he wins if he plays either red or yellow, one of the 2 cards left in his 4-card hand. He doesn't win if he happens to play a green, and there are 2 greens left. So it's a 2 out of 4 chance that he wins either of these. This is really just 1/2. And 1/2 chance that he wins at this point on his third turn, 1/2 chance that, assuming he's made it to his third turn, he doesn't win. Okay? And now, assuming he doesn't win, what are the chances Bridget can win? Well, she will have already had to. So she's laid P and a W, a purple and a white. Anything she picks, she'll win. Okay? She doesn't have a third color, so she guaranteed will win at this point. Okay? So that actually ends the tree, which is nice, because I was about to have to flip the page and draw this a little shorter. Now, what are we asked for? We want Amir to win. Well, there's a 1/5 chance he wins on his second turn. And then, following along, there is a 4/5 times 2/3 times 1/2 chance that he wins on his fourth turn. Okay? So 1/5 and then 4/5 times 2/3 times 1/2. Okay? Now, as I said, some of the stuff I will say verbally with my reasoning as to why B wins with 100% or why it's a half here is something that you should write down beside the tree, but I didn't want to be ping-ponging back and forth. So Amir wins either, not 4/5, 1/5, either 1/5 from winning on his second turn, or, and in probability when we say or, we really mean plus, 4/5 the chance that he doesn't win on his second turn, and then a 2/3 chance that Bridget doesn't win on her second turn, and then a 1/2 chance that he does win on his third turn. Okay, so this is 1/5 plus 8 over 30. Well, the 2's cancel out, so 4 over 15. That'll be 3 over 15 plus 4 over 15. So it's a 7 over 15 chance that Amir wins. Now, something you can do really quickly to double check and make sure at least your numbers are making sense. We know that either A wins or B wins. Okay? So the probability that A wins plus the probability that B wins should add up to 1. Now, what's the probability that B wins on her second turn? 4, and then 5 times 3, so 4/15 is the chance that she wins here. What are the chances she wins here? 4/5, 2/3 times 1/2 times 1 is another 4/15, and that would add up to the remaining 8/15 to complement this 7/15. So I'm happy that the math has worked out. Okay, and so assuming our tree has been drawn correctly and explained properly, we're good to go. Okay. So what have we got for B part? B part, now we've got a fellow by the name of Carlos, and he's got 14 coins, numbered 1 to 14. Each coin has exactly one face called heads. When flipped, coins land heads with probability H1, H2, up to H14. When Carlos flips each of the 14 coins exactly once, the probability that an even number of coins lands heads is 1/2. Must there be a coin K between 1 and 14 where the probability of heads for that coin is exactly 1/2. So they could be coins with various weights. You know, one might be weighted to always do heads, something like that. Okay. So the first thing I notice here, 14 really has nothing to do with it. So we might try, and this is always a good idea, we might try a smaller case. 1 coin, 2 coins, 3 coins, something like that. And then see, is there something we can exploit to get 14 coins? Like maybe only even numbers of coins have the property they want. Or maybe only even coins don't. Maybe there's always a way with even coins to avoid having a coin that has exactly 1/2 the chance of heads. So let's see what we can do. Okay. So we just start small. Okay. So if I tried just 1 coin, right, what's the probability you get heads? An even number of heads. Right? Well, there's only 1 coin, and so if you have an even number, it's got to be 0 heads. And the probability of that would be 1 minus H1. And so if that's 1/2, if the probability of getting an even number of heads is exactly 1/2, then rearranging, you see that, yeah, your only coin does have a probability of getting heads of 1/2. Okay, that wasn't particularly interesting, but what if we tried 2 coins? Okay. So now I've got H1 and H2. Now the probability of getting an even number of heads, it's either 0 heads or 2 heads, because there's more coins to work with. So the probability of getting no heads is 1 minus H1 times 1 minus H2. So neither one turn up heads. And the probability of getting both of them heads, H1 and H2. And we're told this is 1/2. Okay? Now that's a lot of variables, and I suppose we could expand this out. I was hoping the H1, H2s would cancel out. They don't. So there's nothing really we can do there. But we can get another equation. If you don't have an even number of heads, if you have an odd number of heads, then you'll get, so that's got to be the exact opposite, so it'll be 1 minus the probability of an even number of heads. But we were told that that's 1/2. So the probability of getting an odd number of heads is 1/2 as well. And to get an odd number of heads, you have to have exactly 1 head. So this will be H1, 1 minus H2. So that's if the first coin is the one that flip heads and the other one is tails. Or the first one might not and the second one will. And I suppose we could expand this out, but it's also equal to 1/2. And so maybe we can add the 2 equations and get 1, or maybe they're equal. We could subtract them. Who knows what we can do? But we'll expand this out. H1 minus H1, H2, and then H2 minus H1, H2. So we know 1/2 is 1 minus H1 minus H2 plus 2H1, H2. Right, these 2 here. And then we also now know that 1/2 is H1 plus H2 minus 2H1, H2. And if you add those up, everything's going to sort of cancel. So that's not going to help. But what if we subtract one from the other? We'll get 0 is 1 minus 2H1s minus 2H2s. And then 2 minus negative 2, it'll be 4 H1, H2. And this, I think, factors. Yeah, it does. And so in order for this to be equal to 0, one of these has to be equal to 0, and then that would imply, if 1 minus 2h1 is 0, bring the 2h to the other side, h1 would have to be 1/2. Okay, so that would work. And I suppose we could even go back here and say the probability of an odd number of heads. That can only happen when you have one head, and that would just occur with h1. And so now it's also 1/2. So we can do sort of the same subtraction. This minus this must be equal to 1/2 minus 1/2, which is 0. Okay, so this is working out great. Can we sort of work this up to maybe size 3 or maybe jump to size 14? Is there a nice way? So a couple observations that we've made. If the probability of an even number of heads is 1/2, then the probability of an odd number of heads is also 1/2. So the difference in those two probabilities must be 0. And so what we'd like to do is sort of factor this and maybe factor it into 1 minus 2h1, 1 minus 2h2, and so on. For 14, although it really doesn't matter, it could be any number of coins, I think. And then so in order for this to be 0, one of these has to be 0, and so at least one of the h's has to be 1/2. The only question is now, how do you show this? How do you build up? Just because I know it works for 1 and 2 that you can get this factoring, how do you know that we can do this with more? And I think that indicates we should probably use an inductive argument. It won't necessarily be pure mathematical induction, but let's try and set something up, shall we? If we focus on one of the, Now, what is the best way to approach it? I just want to deal with one of the what if we okay. So let us consider So I claim that for h1 through to hn, because we're just going to deal with this generally, if you really care, just change n to 14. Probability of even number of heads minus probability of odd number of heads is, let's see, what did we have? It was 1 minus 2h1, 1 minus 2h2, and so on, down to 1 minus 2hn. And that's what we're going to claim, and then because that's going to be specifically equal to the 0 that we've just pointed out, we'll get this statement as our conclusion, and then one of them is going to have to be equal to 1/2. Okay? So how are we going to do that? So it is clearly true for n equals 1. We did that base case. We also did the case with 2, but we've sort of already done this base case here. But you could say, getting an even number of heads minus an odd number of heads is 1 minus 2h1. There, we're fine with that. Now, suppose it is true for n equals k, and we wish to show it holds for n equals k plus 1. So we'll distinguish sort of our last coin, k plus 1, and we'll look at that. So, what's the best way to say this? So the probability of an even number of heads, so either HK plus 1 is a head, or the K plus first coin is not. Okay. Now, if it is a head and we want an even number of heads, what do the other coins have to be? Well, there have to be an odd number of heads. For the K other coins. And if the K plus first coin isn't a head, then we still need to have an even number of heads. Again, for the K other coins. Okay? But by induction, we know what both the... So maybe I don't have the right induction statement, because I would need... No, this should be fine. Yeah, this should be fine. And then the probability of an odd number of heads. I lost myself for a moment there. So either either the K plus first coin turns up heads, and then you'll need... So you've got one head, you need an even number remaining. Or it doesn't turn up heads, and so we still need an odd number of heads. And again, this is for K plus the K other coins. Okay. If we wanted to, we could perhaps give names to these. Maybe call this Q and this P or something like that. That would be fine. So now, the probability of an even number of heads minus the probability of an odd number of heads, and these are both for K plus 1 coins, is, I'm going to have to write this on the next, so probability even minus probability odd, because that's what we want. We want to find the expression for that. It's going to be HK, and then the probability of an odd number of coins, plus 1 minus HK, that's probability of an even number of coins, minus HK times probability of an even number of coins on the remaining K coins, and then minus another 1 minus HK times the probability of an odd number of coins, and these ones here are on K coins, and we've singled out this should be the K plus first coin. Right, so I think this is probably the best way to write it up. I'm not entirely sure what's the neatest, simplest. I think it's starting to get a little confusing with me writing P even and P even to mean different things. That's why I'm trying to highlight when it's K coins and when it's K plus 1 coins. You might not need necessarily an induction argument like this, but I think this is probably going to go well for us. Okay. So, if we sort of group things together, we'll have HK plus 1, and then P odd minus P even, which I am going to choose to write the other way at the cost of a minus sign out here. And then plus 1 minus HK plus 1, P even minus P odd. Okay. Now I can factor this out, and we'll be left with 1 minus 2 HK plus 1. And then we've got the smaller case, the case just for K coins, not K plus 1 coins. Okay. But by induction, we assume that that holds true, and so that has a particular way of being written. Goes with our sort of hypothesis here. I'm writing the order differently than I had but a moment ago, but that's not really going to be an issue. So okay, now with this and we haven't used the fact that the probability of an even number is 1/2. But now, because the probability of getting an even number of heads is 1/2, and the probability of an odd number of heads is 1/2, and we've already stated this, and we've got this factorization, then this should be equal to 0. And now everything should follow from there. So for n, or for particularly this question, although they don't really care if you do general versions and then say at the end, just let n equal 14. That's why I like doing general cases. But for n coins, we see that 0 is 1/2 minus 1/2. Probability of even minus probability of odd is 1 minus 2hn, 1 minus 2hn minus 1, all the way down to 1 minus 2h1. And we just observe at least one of these factors must be 0. Therefore, at least 1 hi is 1/2. So not only does this work for 14 coins, this works for any number of coins, and we sort of proved it with an induction. Okay? There might be a faster way. I don't think there's a way specifically for 14 off the top of my head. There might be like a fast way because it's an even number of coins or something like that. Taking a look at our case with 2. But I think the induction argument worked quite nicely, and it wasn't that bad. It didn't take us too long. Looking at the case with 1 coin wasn't the most helpful, but looking at 2 coins, that factorization really sticks out, and that was key. Okay, so we just had to show that factorization works for any number of coins. Okay, C part. Serge and Liz each have a machine that prints digits from 1 to 6. Serge's machine prints the digits 1, 2, 3, 4, 5, 6 with probability P1, P2, P3, P4, P5, P6. Why did they use Serge and Liz? You got Q1, Q2 do the same thing. They could have done something like Penny and Quentin. Not even how you spell Quentin. Anyway, I don't see why they didn't do that, but whatever. So Serge and Liz, these are actually probably named after people. That's probably what it is. But Amir, Bridget, and Carlos, that's ABC. Anyway, so Serge's machine, the probability P1, P2 for the various outcomes. Liz's machine, the probabilities are Q1, Q2, and so on. Okay. Each machine goes ahead and it prints one of the digits, and we're going to let SI be the probability that the sum of 2 digits printed is I. And we're told S2 is the same as S12, is the same as half of S7, and we know S7 is positive. So we want to prove that P1, the probability of Serge's machine printing a 1 is the same as the probability of it printing a 6, and Liz's machine has the same thing. Probability of printing a 1 is the same as probability of printing a 6. Okay. This almost looks like dice. It really does, because dice 1, 2, 3, 4, 5, 6. But I guess they would have trouble trying to explain the concept of weighted dice giving very, very different probabilities. But okay, so they've changed it to machines. I don't think, just like 14 in the last question, I don't think the fact that there are 6 outcomes has anything to do with it. So if you'll indulge me, I think I'm going to try and approach this more generally. And I want to try and generalize this problem a little bit. Okay? So here's what I'm going to do. Serge is going to have probabilities P1, P2, all the way up to Pn for his machine printing 1, 2, all the way up to n. If you're upset with this, just make n 6. Okay, but there's really nothing special about 6, I don't think. Now we might start doing some work and then I realize, oh, there's only a special factorization if n is 6, but I don't think that's the case here. It doesn't look like it. Okay? So now, the probability of getting a 2, the only way to get a 2 is if one machine prints a 1 and the other machine prints another 1. So that probability's got to be P1, Q1. Now, if we were using 6, 12 can only happen as 6 plus 6. So what should I replace 12 with if I want to make this question very general? 2n, 2 times the biggest number, because this can only happen if Serge's machine prints an n and Liz's machine prints an n. Anything smaller will not add up to this. And I can see the probability there. And then we've also got S7. So what's special about 7? So 7 would use it would use every single probability here, just sort of pairing them up across like that. So the best way to generalize that is n plus 1. So that'll be P1 Qn. You know, if you can't see how to generalize these sorts of things, of course, just stick with the actual question as written. But I want to try for something a bit more general, because I'm really excited by the way I handled the last question, where it doesn't actually matter the number of coins. So I'm of the opinion it doesn't matter how many outcomes there are. I think it should be the same number for both machines, but maybe that's not true either. Okay, so here's what we're assuming. S2 is the same as S12, and those are all 1/2 of S7, and since S7, or in this case Sn plus 1, is positive, these are all positive. Okay, so what have we got? P1 Q1, P6 Q6 is half of that expression. So just while I'm sitting here looking at this, if we show P1 is equal to P6 or Q1 equals Q6, we can divide. So, you know, for example, if we show P1 equals P6, well, not 6. I guess these are supposed to be n's. How quickly I abandon my generalization without thinking it through. So, so if I had P1 is the same as Pn, then this second statement here is really P1 times Qn. Just divide both sides by P1 and you'll get the other one. So the other is true by division. Now you might say, well, hold on, what if P1 and Pn are both 0? Because then you can't divide by 0 and have these things be equal, but if they were 0, you wouldn't have greater than 0 over here. These amounts wouldn't be positive, they'd be equal to 0. So we'll say the other one is true by division. If you're trying to explain this and you don't think anyone's going to get it, just show as an example if P1 is Pn. Just divide by P1, and then make the comment P1 is not 0, since S2 is not 0. And then you get Q1 is Qn. So, as long as I can show one of the statements they want is true, the other one must be true. And so we are free to then focus on P1 equal Pn, or maybe Q1 equal Qn. I don't think it actually matters which one, though. Okay? Again, you can make some sort of symmetry argument, because if you answer the question for Q, you change all the P's to Q's, Q's to P's, and your argument should still work. In fact, I wonder if we had a third machine. This is just thinking ahead, maybe making an interesting question in the future. What if there was a third machine, you know, Serge, Liz, and maybe David, and his machine prints out R1, R2, R3, and you had the same sort of results? Could we get anything like that? Can you show that P1 and Q1? Probably an induction argument, maybe. I don't know. But I'm not going to generalize it that much. I think you're already being patient enough. So that's kind of an interesting observation. Just from this part of the statement, I know that if I can show one, I can show the other. Okay. And now, since both of them are equal to a half, I can see, okay, a half. I don't like half sitting there. I'm not happy with the fractions. So I can say they both add up to Sn plus 1, or S7 in the original question. So I got P1 Q1 plus Pn Qn is P1 Qn plus P2 Qn plus n minus 1 all the way up to, and then Pn Q1. Okay? Now I don't think I particularly care about the inner numbers. aside from maybe I need to make some observation about them being positive or something, because we don't know enough about them, and we're also not being asked. Nowhere in the question does it reference P2 or Q2 other than that these exist. So I think what we really need to do is focus on the P1, Q1, PN, QN, and where they appear. So I don't really care about this middle part, but I can see P1 is here, P1 is also here, but it's not paired up with the same thing both times. Q1 and QN. We've also got PN, PN, but again, they sort of performed a little bit of a swap here almost. Almost. Okay. So, I'd like to just focus on those ones for a moment. So I'll say it's got to be greater than or equal. I don't know if this middle stuff is 0 or whatever. Okay, so greater than or equal. Probabilities are never negative. So multiplying probabilities that are either 0 or positive, you're only going to get 0 or positive for your sum. Okay. Now, this kind of just because of the way we handled B with all that factoring, I feel like this can be factored as well. Take out a P1 minus PN, Q1 minus QN. Right? Yeah, that matches up. All right, so that's got to be true. Now, what I want to do is show that it has to be 0. So how can we approach it? So we need this needs to be 0. And so how can I show it can't be greater than? Well, naively, if this is greater than, maybe showing that this would have to be less than, something like that, then there's no way to get a positive amount. So we need another relationship between P1 and PN. So if I assume P1 isn't the same as PN, because otherwise we've already shown that implies that Q1 is QN and we're done. There's no reason to assume to think one has to be greater than the other. So if I make the assumption that P1 is greater than PN, and you want to try the other case, you can do the same arguments, just change the n's and the ones. So we're about to make an arbitrary choice. I'm going to say without loss of generality, which is the fancy way of saying the choice I'm about to make isn't really a choice. So without loss of generality, assume, because if they're not equal, one of them's got to be bigger, right? So if P1 is greater than PN, that would mean that P1 minus PN is positive. So I want to show that Q1 minus QN can't be positive as well. And then you wouldn't get this, you'd get only equal to 0, and we'd be all set. Okay? So, by the way, this page is just me sort of playing around. I would probably make this argument and then proceed right into here. And then make my conclusion resemble something like this, but in reverse. Okay, now, how does the P1 being greater than PN relate to Q1 being greater than, or being less than QN? Let's see, the only thing we know for certain is this one solid relationship here. Now, if I multiply by something bigger on this side than this, in order for them to be equal, QN has to be bigger than Q1 to compensate. Now, what's the best way to write that out? So here's what I can say. since probabilities P1 and Pn are greater than 0. Why do they have to be greater than 0? Well, all probabilities are positive. And these ones can't be 0 because S2 isn't 0, which is something we've already used. If P1 were 0 or Pn were 0, then they would be 0, and so S7 or Sn plus 1 would have to be 0, but we've already been told it's positive. So we're really, really making use of that positive thing to ignore probabilities potentially being 0. So then P1 divided by Pn is going to have to be greater than 1, because I can... We're going to break that down. P1 greater than Pn, divide by Pn on both sides. We see that P1 divided by Pn is greater than 1. And I just had to make sure they were positive because the sign needs to not change. So then, we know this is true if I divide both sides by Pn. We get this nice relationship. And so that means that Qn must be greater than Q1. And as a result, Qn minus, well, let's say Q1 minus Qn must therefore be less than 0, bringing this one over to the other side. So P1 minus Pn times Q1 minus Qn has to be less than 0 in this case. And here's where we can now expand things out. So expanding and rearranging, we see P1 Q1 plus Pn Qn would be less than P1 Qn plus Pn Q1. And now if we add all the other stuff back in, we've got S2 plus S12 must be less than or equal to... Actually, no, it would still have to be strictly less than. It would be less than Sn plus 1, but we've already remarked that Sn plus 1 is the sum of those two. So what we've managed to show is the sum of these two values, S2 and S2n, must be less than themselves, which is impossible. Typically in math we say you've reached a contradiction. Okay, so where did this all come from? We assumed P1 and Pn were not the same. And in particular, we said they were positive. If you had the other relationship, then you'd get that these were positive, and you'd still get negative there. That's why our choice, P1 greater than Pn, doesn't matter. That's why we were allowed to say without loss of generality. Okay? So there we go. So this is impossible, and that was our only other possibility. So P1 must be the same as Pn, and therefore Q1 and Q6, I guess, are the same as well. So P1 is P6, and Q1 is Q6. We've just done this a bit more generally. And that was all we were asked to show. So we are done. Question number 10. Okay. So a very nice little paper. I seem to recall, and I sort of share the same sentiments here, I seem to recall when we were reviewing this that question 10 seemed a little easy. But I could definitely see where if you're not making the right connection. So if you didn't, for example, expand out S7 as P1 Q6 plus P2 Q5 and so on, and say, all right, this has to relate to P1 Q1, P6 Q6. I should really ignore the P2 and the Q5. You're not going to see that nice little relationship. You're not even going to think you can factor. And I could definitely see that maybe you having used the relationship S2 is equal to S12 to show that if P1 is P6, then therefore Q1 is Q6. I could see people maybe not going back to that statement to try and show that if P1 is greater than P6, Q1 has to be less than Q6. And that really is something we needed to make that last inequality work. Okay? And just because I saw it doesn't mean that everyone necessarily would see it. But I recall seeing that pretty quickly when we reviewed it. And I think I was a little faster than what I've written here, but that's okay. But yeah, I would say that was not a bad question 10. Very, very interesting probability questions, but not particularly difficult. Maybe it's a matter of the time. But I liked that 10. I didn't find it particularly too much of something I just had to push through. I was even able to generalize it a little bit. But anyways, that's it for the 2019 paper. If you're looking for any more Euclids, feel free to browse around the channel. You know, if you want to look at last year's, 2018, or the next year, the 2020, whenever that gets uploaded, feel free to stick around. And if you want to be kept up to date, feel free to hit the subscribe button, but no pressure whatsoever. I'll still be here regardless, doing more math contests. Speaking of which, I think I'll start recording another one, so I'll see you for more math in the future. Take care.